right, I think we're going to go ahead and get started. Is the Zoom thing, is the recording on? It's okay. All right. So I'm going to try to pick up where I left off, but in order to do that, I need, because we all went away and ate lunch, and you don't necessarily remember everything from before lunch. I want to remind you of the calculation that you've seen from a couple of different points of view today. So the first, we are considering an effective field theory for particles, fermions, let's say, interacting via a short-range potential. And we postulate that the leading order in this effective field theory can be described by this Lagrangian. So we do the normal thing. We go ahead, we write down Feynman rules, we calculate diagrams, we use dimensional regularization with minimal subtraction, and we get this result at leading order and this result at subleading order. And then, hang on, let me make sure I've got my minus signs in the right place. Yes, okay, that's what happened. I need a minus sign here. So then, I need a minus sign here and here and here. And then this, sorry, I shouldn't say subleading order. We can calculate loop diagrams, and in this case, we can calculate all the loop diagrams because this is a very easy effective field theory to solve, and the result for the 2-to-2 amplitude involves a particular subset of diagrams, namely these n-loop diagrams like this, where there are n loops here and n+1 vertices. So if we calculate this using dimensional regularization and minimal subtraction, we get this. So then we sum these because this forms a geometric series, and we get this. We do a little bit of algebra, and we require that this goes in the limit as k goes to 0 to minus 4 pi a divided by m, where this sign is conventional. But this sign ensures that the scattering length has the usual interpretation in non-relativistic quantum mechanics, namely that it's positive for a weak repulsive potential and negative for a weak attractive potential. So if we require that this be the experimental result and we have a number for the scattering length, then that fixes the value of this coefficient C. All right, so that's where we got up to before lunch. So now I'm going to make a few remarks about what happens if A goes to infinity. So Professor Kaplan mentioned this as an interesting limit of this theory. He pointed out that in this limit, the theory is fine-tuned, and this can be regarded in some renormalization group sense as a fixed point of the theory. So you can approach the scattering length going to infinity. You can either approach it from the side from which there are no bound states, in which case you start off with no bound states, and then if I think in terms of Professor Kaplan's picture of the scattering length, what was this? A over delta as a function of the coupling strength, right? We had so if this was for a square well, so this point here is the point at which the first bound state appears. And when the first bound state appears, the scattering length will approach, I guess I've drawn this, sorry, I should have started here at 0. Apologies. There we go. And the first bound state appears here, and so A will go to minus infinity. But we can also approach it in the other direction by starting with a bound state and making the potential weaker, in which case this limit corresponds to the bound state disappearing, becoming shallower and shallower and shallower and shallower, and then disappearing through the threshold and becoming a virtual state. No matter how we approach it, whether from the left or from the right, this point here is special. At this point, the scattering amplitude looks like this. And this is called the unitarity limit. It's called the unitarity limit because the only thing that's left is this IK piece that is required by probability conservation. One way to think about this limit is that the scattering is as strong as it could possibly be. You've saturated the bound on the amplitude that is imposed by probability conservation. In this limit as already, so now the pole, if we think about the pole of this amplitude, as already commented, there is a pole at k equals I times, you can either say it's either I times 0 plus, by which I mean it's approaching from the positive energy axis. That's if we come from above. Or it's a slightly negative if we come from the other side. But right at the unitarity limit, there's a zero energy bound state. This amplitude has no physical scales associated with the system left. So if you think about what we've done here, we constructed an effective field theory with a zero range interaction, a delta function. Then we tuned the scattering length to infinity. And so in this limit, there are no physical scales left. So this actually means that all amplitudes in the theory have to go like powers of the scattering momentum k, because there are no non-analytic functions left over for us to calculate. There's only one scale, there's only one physical parameter, that's k, and every amplitude is just a function of k. You can actually compute many of these functions, and this is a program that's been executed by Dam Son and his collaborator Hans-Werner Hammer, using this fact that this is a scale invariant. This field theory has to have scale invariant. So it's a scale invariant non-relativistic field theory. And so it actually has what's called the Schrödinger symmetry, meaning that it has a dilatation and conformal symmetry in addition to Galilean invariance. So it's a very interesting limit to think about also from a symmetries point of view. You might think that this is an academic exercise, but as Professor Kaplan pointed out, the scattering length between two neutrons is about minus 18 Fermis, which is much larger than the range of the nuclear force, which is, as I mentioned, a couple of Fermis. And so that means that there is actually a window in the scattering of neutrons where this unitarity limit is realized. You basically need to live at momenta that are large compared to 1 over A and small compared to 1 over R. And if you do that, then the amplitude will look approximately like this. Other people have used this Schrödinger symmetry to compute, for instance, the properties of the thermodynamics of neutrons when they satisfy this condition. So multi-neutron systems. The one thing that is interesting, for instance, is if you collide neutron-rich systems on an alpha particle, these experiments are done at Riken in Japan. You can produce multi-neutron systems in the final state. You can produce 2 neutron systems, 3 neutron systems, 4 neutron systems, and then measure the properties of the final state interactions where these neutrons are close to this unitarity limit. And that's an ongoing experimental program. All right, are there any questions about the unitarity limit before I move on to a different topic? Meaning? Yeah, okay, so if I did this in MS, C would be infinity, because C would be 4 pi over m, right? And then as already discussed, the nucleon mass is not really a scale. You can actually, by doing a field you can redefine the fields to remove the powers of the mass from the theory. So yes, in this limit, you can actually write, if you choose a particular scale-independent scheme, then you can actually see this symmetry in the Lagrangian. Yeah. Other questions?
That limit then it becomes a trivial sort of.
It's not trivial, right? Right, exactly. It's not, so the scattering is as strong as it can be, right? It's a little bit mind-blowing to think about. So this is actually, one thing I find very amusing about this is that, I don't know, maybe a little more than 15 years ago, Howard Georgi proposed this concept of unparticles. So these would be fields that had no dispersion relation because their propagator looked like this, and he pointed out that this would occur in scale invariant theories, but he was thinking about the relativistic context. And so far we have no example in a relativistic field theory, at least that I know of, where this is manifest in nature. But actually in the non-relativistic field theory, the neutrons are actually an example of this sort of unparticle concept, because the degrees of freedom associated with this, like if I think about this as the propagation of a bound state, the dispersion relation of the bound state is very weird because I just have this IK thing sitting downstairs. It's not a K squared minus M squared, or there's no, yeah. Okay. So let's push this through a little further. Let's indeed think about the degree of freedom associated with the 2 neutron state, or more generally a 2 nucleon state. Let's think about that as an actual field in our theory. So the irony of what I'm about to do is that this formulation of the non-relativistic EFT was developed by David Kaplan in 1997. So, but I'm the one who's going to talk about it, but that's okay. He said I could. So for those of you keeping score at home, as they say in the baseball world, baseball, by the way, is a good substitute for cricket if you ever get stuck in America and are deprived of cricket. But you have to remember that baseball is for people with short attention spans, because it only lasts 3 hours, not 5 days. Okay. This joke doesn't work so well in the 2020 era. So yeah. Okay. All right. So for those of you keeping score at home, we're going to do the Hubbard-Stratonovich transformation backwards, I guess, to rewrite that Lagrangian in terms of an auxiliary field. So D is the auxiliary field. We'll call it a dimer. Sometimes people also call it a dibaryon. I don't care what you call it. It's just, I'm going to use D to represent it. It's the auxiliary field associated with the 2 nucleon state. So what are the Feynman rules of this theory? So now we have a vertex. Which way do you want time to go? You want it to go this way? Okay, so this is the vertex associated with 2 nucleons coming in and forming this 2 nucleon state. Right. And then the Hermitian conjugate gives you the breakup of the dimer into two nucleons, and then propagate. So this is, sorry, Feynman rule. And then the propagation of this thing at tree level is just I divided by delta. And then straight away, if you're quick, you can see how to do the Hubbard-Stratonovich transformation at the diagrammatic level, because now if I, again, this is another one of these field theories where you can actually solve it exactly, because there's nothing else that can happen other than this gets formed. Once it gets formed, there's no other vertex in the theory. Everything's non-relativistic, so the only thing that can happen is it can break up. So what is that? That's minus I times a constant. This is really a local interaction, which you might think is weird since I have some degree of freedom here, but the key is that at the moment anyway, this degree of freedom has no kinetic term. So this dimer gets formed, it sits there and does nothing, and then it breaks up. It is, you might think it is completely useless, right? What's the point in having something that gets formed, doesn't propagate, and then breaks up? And indeed, there's nothing at this level that's superior to this formulation over this formulation. The fact that this is not dynamical and doesn't propagate means that this is completely local. And so this is exactly the same thing as having minus I times C. I'm going to, Abhishek, can I ask a question? So would you call this an auxiliary field regardless of whether you give it a kinetic term? Or is it only auxiliary field if it doesn't have a kinetic term? Okay, so he uses them more than I do. So he says if either way, it's an auxiliary field. But it's only exactly equivalent to that Lagrangian if it has no kinetic term. I would say it's a field that you introduce to capture some set of, let me answer at the two-body level. So at the two-body level, it's a field with baryon number 2 that you introduce in order to capture some set of baryon-baryon interactions.
The same as having filled with infinite function.
I'm not sure I'm familiar, but.
Like the kinetic term and the function.
Okay, yeah. Oh, you're saying that doesn't propagate. Maybe, yeah, that's probably true. Tomorrow I'm going to make it dynamical. And then you will see that if the advantage, then we get to some advantages, because then you can go looking for poles. Actually, we can already do this. The point of this is if you want to go looking for bound states, then you can think about computing the DD correlator. And that correlator, poles of that correlator will correspond to two-body bound states. So it doesn't appear, that's right, it can't appear as an in or an out state, but you can still calculate the DD correlator. Right? And then poles of that correlator will correspond to bound states. So it's a neat way to go looking for bound states. If any of you do lattice QCD, it's like you can think about this as writing down an interpolating field for the two baryon state. Right, so. It is not the mass difference because it is scheme dependent. It's scheme dependent, but you can, as you'll see, you can think about it as some sort of bare mass, or maybe bare mass defect would be better, since I'm trying to make this distinction between nuclear physics and, yeah, okay? Yep. All right, so let's do that. Since I said that this was the whole point, let's compute the dressed D propagator. So I guess this isn't a new section, so I'll do this. So what does that look like? So I have this plus this plus this plus blah, 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 blah. And pretty quickly, you're going to realize that this is just another way to say that this whole thing is that the amplitude is a geometric series. But of course, here you have this elegant feature that I have too many Ds. That's my problem, right? Okay. If I compute the propagator of this dimer field in its center of mass frame, I'm going to get where I've defined the self-energy in the center of mass frame to be minus Ig squared times our favorite integral, okay? So now we have a slightly different interpretation for this integral. We're going to think about this as the self-energy of the dimer field. So if you, so now this relates to your question about whether you can see this in outstates. You don't see the dimer field in or outstates, but of course it couples to things that you do see. So the amplitude for nucleon-nucleon scattering is just minus Ig squared times d, the propagator. Because the only, as I said, the only thing that can happen is particles come in, they form the dimer, they go out. So you just need to multiply by 2 of these to get the effect of this stress dimer field on the amplitude. And then you discover that you get, of course, you get something that's completely equivalent to what we did before. If you compute the self-energy in ms. If you compute the self-energy in ms, you get the same thing we got before, minus Imk over 4 pi. And then you see that you have this relation here. And then you will, and then in order to make things match, you will have to have g squared over delta to equal 4 pi a over m, which should be, because I told you that this should be completely equivalent with the identification that g squared over delta is c. So why is this useful? It's useful for a couple of different reasons. One reason is because, as I said, tomorrow we're going to compute properties of 2 nucleon bound states. And now I can think about computing like the 3-point function of a dimer coupling to a photon. And that's going to be related by just factors to the form factor of that 2 nucleon bound state, right? I can compute, I don't actually need to solve the full amplitude to figure out where the poles are. I just need to solve this equation to figure out where the poles are. So that's a little bit simpler, at least conceptually, than solving for the full amplitude in order to find the poles. And the third thing I find useful here is that this provides a natural connection to the physics of resonances, which we'll be discussing maybe tomorrow, maybe on Wednesday. In particular, what you see here is that, let me rewrite this in a slightly different way. What you see here is that you only need to resum the self-energy if you are not, I don't want to say this. Yeah, okay. So if the bare propagator is close to 0. So let me say this a little bit more slowly. So there are a bunch of diagrams here. And this diagram is 1 over delta ms. Now, if the scattering length was small, then this would already be a big number, and all the other corrections would be perturbative. But in the limit that the scattering length gets large, then, did I get this one the right way? Sorry, yep. Let me go back a step. So in the limit that the scattering length gets large, I need to resum all these diagrams because this diverges. Right. So when this diverges, so yeah, I said that the wrong way around before. So if the scattering length is natural, then this quantity is small, right? And because the scattering length is small, and then this is a perturbative series. But if I get close to the situation where the bare propagator blows up, in other words, I'm close to the unitary limit, then I need to consider these corrections. So this is actually something that you do in quantum field theory on a regular basis. If you have an infrared pole in your theory, you have to resum the self-energy diagrams to find out what happens to it. So this is the way I actually think about the unitary limit now and about all resonances in effective field theories, is I think about it as there is a situation where the bare propagator blows up. So you have a pole, if you don't compute, you have an infrared pole, and then you need to compute all the loop corrections to the infrared pole, and all of these diagrams in this series are the same order. So you need to solve the Dyson equation for the propagator, and then you find out what happens to the infrared pole after you resum that series. So I find, and I will come back to this interpretation when we're talking about resonances for P-wave systems in a day or two. No symmetry, it's a power counting argument. So when I introduce it, the kinetic term will be proportional to the effective range. Okay, so yeah, so it's not, there's no symmetry that prevents it, right? Yeah. Yes, all right. All right, so then in the next, okay, so for the next 20 minutes, I'm going to talk about I'm actually doing my, I realize I'm doing my lectures in the opposite order to Professor Kaplan. So he started with non-relativistic quantum mechanics and then went to field theory. I'm going to connect what I've been doing to potentials. All right, so, okay, so as Professor Kaplan pointed out, what we want to do here is solve the Lippmann-Schwinger equation. And so in general, I could write the Lippmann-Schwinger equation like this, up to a sign. I'm not going to worry about the sign here. The sign actually has to do with exactly this convention I mentioned before about whether you take A to be minus 4 pi A over M or plus 4 pi A over M. But if you want to know more about that, ask me in question time. So the potential that we have is a constant when I take momentum space matrix elements of it. All right. So maybe, I don't know which, all right. So this is always a fun exercise. So who thinks more clearly in momentum space in this room? So everybody that I've met either prefers momentum space or coordinate space. So it's always I claim that I am bilingual, right? So we'll see if it's the only sense in which I'm bilingual, unless you count Australian as a separate language. Okay, but almost everybody has a preferred space in which to work, right? So who prefers momentum space? 1, 2, okay. And who prefers coordinate space? All right, well, I'm going to make you all happy because we're going to move backwards and forwards smoothly between them, okay? So this delta function interaction that we've been blah, blah, blahing about, for those of you who apparently are the majority who prefer momentum space, in coordinate space, it's a constant. And you can see this because if you extract the interaction from the Lagrangian, it's just a number, right? So, you know, Professor Kaplan wrote it in coordinate space, but if you wrote it in momentum space, it would just be a number C. You can also see it, and maybe we'll do this as an exercise in the next hour after the coffee break. You can also see this because this is the Fourier transform of a delta function. So if maybe you can see this trivially, but this means that this thing is not only local, but it's also a delta function. Right? So all right. So this potential is a very simple example of a more general class of potentials called separable potentials. Separable potentials are potentials that, wait for it, separate. So general form of a separable potential is that there's some function of P times some strength times the function of P prime. This one is very simple because the functions are 1. There's a lot of interest in the separable potentials in like the 60s and 70s because they made like 3-body and 4-body problems computationally tractable. For those of you keeping score at home, you can think about this as the first term in a finite rank approximation to the potential. All right, so what is nice about separable potentials is that the Lippmann-Schwinger equation factorizes, just like our equation factorizes. So in this case in particular, if I think about taking momentum space matrix elements of the amplitude, because this G0 is 1 over E plus minus the free Hamiltonian. So in non-relativistic quantum mechanics, that's just this thing that we keep writing down, the 1 over E plus minus P squared over M. And then the integral that if I take matrix elements of this equation, I get the integral form of the Lippmann-Schwinger equation. Uh-oh, I'm going to violate the rules. Oh, can't do it. Sorry, I should have put the integral on the previous line, but it's not going to matter. Okay, so really this integral should be up here, because I'm integrating for a general potential, I would have to integrate over the momentum dependence here and the momentum dependence of the amplitude. But in this case, the fact that the V is constant means that the amplitude is also constant in momentum space. And so we can pull both V and A outside the integral and we get left with our favorite integral that we've been talking about all day. Never have I seen so much discussion of one integral. All right. So this is all just to convince you, if you need convincing, that this thing that we've been calculating all day is just the non-relativistic amplitude. Because another way to think about what you're doing when you sum all those loops is that you are solving this integral equation. It is a trivial integral equation. Well, it's an algebraic equation, not an integral equation. That's what having a separable potential does for you. Again, in minimal subtraction. But basically, whatever you do for the loop, this is what you'll get. You'll get something that looks like this. So the fact it's a geometric series is not special to the minimal subtraction scheme. It'll be true in any scheme you use to calculate that loop. And you get back the same answer I've been writing down many times. Now, what I want to do is to use this correspondence between momentum and coordinate space to tell you to give you a coordinate space picture of what's going on. So I already said that V is A local and B a delta function. So what does that mean? That means if I write down the coordinate space Schrodinger equation, we're doing S waves, so there's no centrifugal barrier. We have a very simple form for the kinetic term. This is just the Laplacian in 3 dimensions. As I said, there's no centrifugal barrier because L equals 0, and then this is the potential. You all remember this from like quantum mechanics class, however many years ago that was. More years ago for some rather than others. So now, like I just actually did a little 20 minutes on delta functions with my E&M graduate class. And I said, and so what is the most important thing about a delta function? There are two things you need to know about delta functions. What's the most important thing? Well, tell me anything you know about delta functions. It should integrate to 1 over any volume, including, in this case, r equals 0. Good. Okay, and what's the other thing about delta functions? Everywhere except where r equals 0. Good. Okay, so I would claim that's the most important thing because that's, you know, almost everywhere. And the other thing is only tells you what happens at this special point. But they're both very important, it's true, right? Thank you. Okay, so what does that mean here? So the fact that this is only non-zero for r equals 0 means that if r does not equal 0, sorry. I keep writing it with a vector, even though I already told you it was S wave, so it's not really a vector, but fine. All right. If r is not equal to 0, this is the Schrodinger equation we're solving. What do we call this equation? It's the free Schrodinger equation, right? So what does that mean? That means that everywhere except at r equals to 0, the particles are not interacting. Shocking, right? Since we said it was a contact interaction. But it means something else. We know how to solve the free Schrodinger equation. So if we have, so pretty straight away, all you need is a little bit of quantum mechanics class to know what the solutions of this are going to be. So I'm going to say that there's a J0 of Kr, which Dr. Kaplan explained how you get that earlier today. And now I've got to find, there we go. I leave notes all over the room and then I can't find them. And then I'm just trying to figure out how I want to do this. Yeah. So it's going to, so we could also have, the Neumann function, the irregular partner of the spherical Bessel function. So if E equals 0, this is the solution, and the scattering length is just the ratio between these two solutions. And then for bound states, we have just the exponential fall off, and because I'm working with the wave function, not the reduced radial wave function u, I have a 1 over r downstairs. So these are the solutions that we want the thing to have. This is for r, this is basically for any r greater than 0. So now you might ask yourself, well, what happens at r equals 0? And here is where you exactly get into the problem that you have some function which all you know is what it integrates to. So in order to answer that question, it's useful to go back to something that Dr. Kaplan did this morning and define your potential to be the limit of a bunch of square wells. Because you know how to think about those and how to solve those. So now, what is this delta function doing for you? It's basically creating the attraction to make your wave function turn over so that you get a bound state. That's at least the way I think about it. So let me switch to U of R, since probably we're more used to seeing pictures of that. Just a reminder, this is just where the square root of 4 pi comes because I have a y0, 0. So this is inside the potential, this is outside the potential. If I'm looking at the wave function for E equals minus B, where the bound state is, this will fall off exponentially. But the standard boundary condition for U, not for psi, but for little u, is that U should go to what? If we want psi to be finite at r equals 0, what do we want u to go to as r equals 0? 0. So it has to start here. So this potential is going to have to make the wave function do that. It has to have enough attraction to make the wave function turn over and have a log derivative that matches the bound state wave function. And then as we pull this in closer and closer, this thing has to happen in a shorter and shorter distance scale, which is why the potential has to become more and more attractive as we pull this closer and closer in. So if you sort of work this out, you discover that so in general, the log to match the log derivatives, the log derivative is to match the log derivative at the boundary, we want this to be minus gamma. But as we take, as r goes to 0, as you can see here, our wave function from the outside is tending to, I should have written proportional to here, sorry. Our wave function on the outside tends to something finite. Yeah. So as we pull this further and further in, this u becomes finite. And so the Schrodinger equation that you are solving here is a Schrodinger equation in which everything is completely normal at r greater than 0. It's just the free solution. But at r equals 0, you have a non-standard boundary condition. You don't have u going to 0 as r goes to 0 because the delta function means that you can't guarantee that the standard boundary conditions of quantum mechanics apply. And the boundary condition you have is actually given here, and that u goes to something finite. So these are the boundary, you don't actually care what this is, you've changed the standard boundary condition that u equals 0 to a boundary condition on the logarithmic derivative at r equals 0, because in the limit that the delta function has its range taken to 0, this boundary condition will be imposed right at the origin. So what's the wave function then? The wave function then is just that. This is u, not psi. So psi diverges at the origin in this theory. That's what the delta function does. You might think that this is not proper, but you can formulate a Hilbert space. This is what's called a self-adjoint extension of the quantum mechanics for r greater than 0. So you can formulate a Hamiltonian that defines a self-adjoint operator on a space of functions that lets you proceed in a quantum mechanically sensible way. And you sort of know that this is true because you can do a whole bunch of calculations for finite range potentials and take the limit, and all of those calculations are sensible. So what does this calculation illuminate? What this calculation illuminates is that what we have here is a theory that describes the tail of the wave function. The theory describes beautifully what's going on out here outside the potential. And to go back to Dr. Kaplan's original statement, we are completely lying about what happens inside the potential. We are doing systematic lying about this. Because we're saying we don't care how wide the delta function is, the square well is, and the only thing we care about its strength is that we're going to tune it so that we get the right fall off here. This is fine, but this is completely blurred in the spirit of effective field theory. You haven't resolved the interior of the wave function, and in fact, you've replaced it by the asymptotic wave function. This actually tells you that this theory is going to be good for systems that are tail dominated. So I actually don't think about this just as the pineless theory anymore. I think about it as an EFT for tail dominated systems. And you might say, well, that's not, you know, such systems are rare, but they're not as rare as you would think, as I was trying to argue at the beginning of my last lecture. And they are fascinating systems because they are systems that are only bound because of quantum mechanics. Right? So these systems, by definition, they don't exist because most of their wave function is outside the potential. They are systems that would not exist if you made a classical argument about what kind of system they were, because the classical argument would tell you that the classical turning point is at the edge of the potential. And since they're dominated by the tail, that means the classical argument misses most of what's going on for these systems. These systems don't just occur in nuclear physics, they also occur in atomic physics near Feshbach resonances, and the X, Y, Z exotics that some of you are probably interested in are also examples of these systems. All right. So in my remaining few minutes, let me start to tell you how to do corrections to leading order. And some of this Dr. Kaplan already mentioned, so hopefully this will be a little bit of review. So the first thing I want to say is that at leading order, results are independent of the range if properly renormalized. So this is related to a couple of questions I got about, you know, where's the range in this answer, or whether we should make the dibaryon dynamical or not. Leading order is designed to capture the infrared physics, and the infrared physics in this problem is the physics of the scattering length, or equivalently the shallow bound state, and the momentum k. So I would say that leading order does a nice job of capturing the infrared scales. It gives you the correct functional form for the amplitude as a function of the infrared scales 1 over A, or equivalently the binding momentum of the bound state and the scattering momentum K. So then the ultraviolet physics, the high energy physics, because everybody's high energy is someone else's low energy, of the finite range interaction the ultraviolet physics of the finite range interaction has to come in through these subleading corrections. And so we're going to try and organize that perturbatively. NLO and squared LO corrections. So the goal is to organize as a perturbation theory. So what will we have? Then the idea is that we'll have a full amplitude A, which is now not just the leading order amplitude in the EFT, which is this leading order amplitude that we already computed, minus 4 pi over m, 1 over, and then there'll be some piece here that is schematically suppressed by powers of these things, which are the expansion parameter. And it's that, and then sort of times leading order. So then the ratio of NLO to LO is set by these things. I'm playing a little fast and loose with my little r's and big R's. I'll say more about that in a minute. Is set by these dimensionless ratios, and it's these dimensionless ratios that determine how well this theory is going to work for your system. And this one we just talked about. This is basically how much tail there is in the wave function at 0 energy. And this And this one, R0K, is whether you probe the interior or not. So if the de Broglie wavelength becomes comparable to the range of the interaction, then you shouldn't really describe the interaction by a crude delta function anymore. So, good question. So thank you. You blew my cover, right? So R0 is what Dr. Kaplan defined. This is the effective range. So this is a number that appears in the scattering amplitude. And capital R is the range of the potential. So generically, little r0 is of order capital R, but the number of order 1 that appears out the front is different depending on the shape of the potential. Okay, so I'm playing a little fast and loose with that here, but when you think about leading order, you think about this capital R because you're thinking about taking some range to 0 or something. When you go to subleading order, you have to renormalize in terms of some physical observable. And so you renormalize to the effective range because that's a measurable thing in experiment. Okay. No, but David did, but I will do it again. But it's not fair to expect you to remember from 3 hours ago. So let me do that, and then actually I think I will stop because we already had a lot of information today, and I think it'll be good to take questions. Okay, so maybe this will let me answer a question that came up as well. Okay, so you remember that this A is related to the scattering amplitude F by, again, up to a sign. I'm playing fast and loose with the signs here. 4 pi over m times F. And if you go back and look at your notes from Dr. Kaplan's lecture, first lecture this morning, I think it was, he said that F was 1 over k cotangent delta minus IK. And then this k cotangent delta, this thing is, this is an analytic function of k squared. Right, so I will say this again, right? So you can show, Beta showed this, for example, but there are more general proofs as well, that this thing, the whole thing, is an analytic. So the phase shift is not an analytic function of k squared. Cotangent delta is not an analytic function of k squared, but k cotangent delta is. Sometimes it's called the effective range function for this reason. And so you can expand it in Taylor series because it's an analytic function of k squared around k squared equals 0. And this r0 over 2, again, the 1 over 2 is conventional. This is the effective range. So this is, if you like, so if you say that the scattering length is how the phase shift comes in to k equals to at 0 energy, then this effective range is basically tells you how that changes as you move away from 0 energy. So what does that mean in this context? Well, this amplitude, for example, that I wrote, this is conveniently sitting here right in front of me. This is 4 pi over m, 1 over a plus ik. So again, up to a sign, because I think there's actually a minus sign here. Up to a sign, now that I put the minus sign in, I think this is going to work. So if I put this minus sign in, then if I set the effective range to 0, I get the leading term in the effective range expansion. So I recover, after all this effective field theory, blah, 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 I recover Beta's result that I can write the amplitude like this at low energy. But then what I can do is insert 2 derivative operators like David was doing at the end of his second lecture, and I can show that those operators give me this term. And then 4 derivative operators would give me this term, and so on. So I can recast this statement about the analyticity of properties of the amplitude as an effective field theory, where the organization is now in terms of a bunch of operators of higher and higher dimension because they have more and more derivatives. Okay, so with that, I'm not going to do that today. I will start, since this seems like a good place to stop, especially because the counter is ticking down and it's about to get angry with me. And then tomorrow I can just start by saying, okay, so let's put in these two derivative operators and see how we do the calculation. And then we can talk about how to push that through then to do both leading order and next to leading order calculations for bound states. Okay, I will take questions. Or we can just go and have tea or coffee, as you prefer. I think it's on now.
When you are considering the potential in momentum space, that is the separable potential.
Yes.
So is the what is the reason actually, or basically why we are considering the separable? It's just to handle mathematically easy, or if I consider, suppose if I handle easily also for the local, not the separable, or then what is the physically difference between the separable or?
Good question. All right, so were you a momentum space person or a coordinate space person?
Momentum.
Okay, so you should want, so here's my argument for you. So my argument for you is, if this EFT is going to work, you have to be able to not care exactly what potential you pick. So pick a potential that makes your life easy. In momentum space, the potential that makes your life easy is a separable potential. So pick a separable potential. But let me also emphasize that, strictly speaking, the Lagrangian gives you a separable potential. Right? If I think about L as kinetic term minus potential, right? Then if you extract this potential here by amputating the external legs, so right, this should, I mean, this thing here is minus IC, right? So the potential is just what this interaction is between the particles. If I amputate the external legs, that's a separable potential. It is the most simple separable potential you can write down. It is a constant. But even if that, yeah. But I also think that that's fine, because the whole point of this exercise is to figure out that we only care about one number in this, one physical number. It's either the scattering length or the energy of the bound state. They're equivalent at this order, right? And so you can take whatever potential you like, as long as it's A, short-ranged, and B is tuned to reproduce that number. All right. If you had, so does someone want to ask me the same question? Who's a coordinate space person? Who's a coordinate space person? Okay, go ahead, ask me the same question. Should it be separable in coordinate space? No, because the Schrodinger equation in coordinate space for a separable potential is not simple. But the Schrodinger equation in coordinate space for a local potential is simple. So you notice when I went to coordinate space, I didn't pick a separable potential, I picked a square well, which is totally not separable, right? It's local, but it's not, right? This one, C, is special because it's both local and separable, which I think is like maybe the only possibility to do that, right? Because otherwise they have to be non-local. Okay. But that actually says that you can go away from the strict delta function limit in two ways. You can stick with the separability, or you can stick with the locality. And I would say which one you do is sort of a function of whether you want to solve the problem in momentum space or coordinate space. Yes?
So previously you wrote this Lagrangian, I think you erased it. So one with the auxiliary fields.
Oh, yeah, I did erase it, yes.
And you called it as alternative formulation.
Yes.
For this Lagrangian.
Yes.
So in principle, if I start from that Lagrangian, I could get back to this contact interval.
I claim that they are, I mean, we can do the math after the coffee break if you want to, right? You can actually do the Hubbard Stratonovic. You can integrate out, it's a Gaussian integral to integrate out the dimer field. And so you can show that if you integrate out the dimer field, you get this.
Exact 4 fermion.
It's exact. The Hubbard Stratonovic transformation is exact if there are no kinetic terms for the dimer field.
That's why the auxiliary field.
Yeah, so there's nothing, I mean, how to say this? I went through the calculation in the two-body sector. And there you can just see it diagrammatically already with this argument that the only mechanism you have is formation and breakup of a dimer, and the amplitude for that matches exactly this minus IC. Right? But if that doesn't do it for you, you can also do the path integral over the dimer field analytically because it's a Gaussian integral. You complete the square, and that's the term you need to complete the square. Yeah, please.
So what cheaper trick is just write down the equation of motion for it. 40. So you get n and there. Substitute it back, you have the same.
It's also right. So yeah, there are like yeah, there are three different ways to do it, I guess, right? Yeah. All right, and next week, I guess, oh, sorry, later this week / next week, Dr. Mohapatra is going to use auxiliary fields all over the place for all sorts of bound states, right? Because he wants to go looking for exotic bound states, and it's easy, I guess this is a fair statement, right? It's easier to find them in the auxiliary field formulation because maybe you only care about is the bound state and you don't care about the scattering amplitude. So you just want to focus on the propagate. You just need an interpolating field that has the quantum numbers of the bound state you're looking for, and then you compute correlators of that interpolating field, and then you can find the bound state you're looking for. Okay. All right. Ebert. So okay, so maybe we should take a vote, right? So I have so maybe make it optional, right? So I have exercises that I can put up on the board and that people can try and work out if they're interested. I wrote down like 6 of them this morning, which are basically things we didn't actually calculate during the lectures, right? So, but I also recognize that it's a long time to sit here and listen to people for 4 hours plus and stay switched on. So if you don't want to come back, that's fine as far as I'm concerned, right? So I will hang out here. And then I guess we have the Q&A after that, right? So, all right, so yeah, we could do it the other way around. We can do the Q&A and then maybe we can integrate them. And so if people have, at some point I may just say, okay, so someone asked me a question that actually, for which the answer is a calculation. Say, okay,
these guys come to the
okay, let's do, well, that might not be fair, but let's say, let's get into groups and do the calculation to see what happens, right? Okay, so how about we can do it that way, and that, yeah, okay, and then